Hello, welcome to the third installment of our videos on Calculus Maxima Minima. So today, the aim is to apply the framework that we've set up in the last two videos to some harder questions. So just to, I guess, recap for Calculus Maxima Minima, the framework is very straightforward, and it's surprising how many of these questions fall into it, where the first part is clearly prove the, now equation is one way to put it, the equation that will to differentiate in part two. And this would require you to basically either use measurement, like volume of the sphere, volume of the cylinder, or in the first example, some similar triangles. But basically, whenever you have an equation where there's two variables at play, make one letter the subject, sub it into the other, and then you have hopefully the thing that they want you to prove for 2 to 4 marks. And then part two sounds obvious, but basically we're going to find the max or min depending on the question, and this generally involves three or four steps. First step is to differentiate the equation. Second one is to solve the differential equation to find the values that you want to then test for max min. And last but not least, sounds obvious, but answer the question. So if the question is asking for find the radius that maximizes a sphere, then you find the radius, but sometimes it might say find the volume itself. Or in the last video, there was a very difficult question at the very end from James Roos, where they basically asked you to find, I believe it was the show that it was an equilateral triangle, etc. So basically answer the question is the last step, and generally this part in part two is worth about 3 to 5 marks, or maybe even more. So let's have a go at a few of these questions. The first one's from Caringbah, 2017, and I say it's from Caringbah. It's commonly scattered through many past papers, whereby it involves a cone where there's a cylinder embedded inside. Now, to do this question, let's see what we've been given, right? So I have a cylinder of R and H. That's the cylinder inside, R and H being variables. So basically you can picture the cylinder radius increasing, which means the height goes down. And it's inscribed in a cone where base radius of 6 and 20 of radius and height respectively. So the 6 and 20 are fixed, and the R and the H of the cylinder is variable. So let's look at the questions that we need to answer. Show that the volume of the cylinder is given by this. Now you can see the volume formula has only one variable R, whereby we know that the volume of a cylinder normally is area of the base, pi r squared, times height. So then that naturally tells us that the variable H needs to be replaced with a function of R, right? Expressed in terms of R. So somewhere in this diagram, we need to find a relationship between H and R, right? That's how we do it. And then part two, classic framework question, and falls in the framework. Find the value of R and H so that the cylinder is max, right? So we'll see which way we use the test for max min. We either go the table method if it's too hard to differentiate, or we use the second derivative. All right, let's do this. So part one, show that the volume is that. So we know volume is pi r squared H, right? Everything starts from this formula. Now, in this diagram, the best way for you to see the relationship is using similar triangles. So I wonder if it's obvious to some of you where there's a triangle there. Can you see the two right angle triangles at play, right? Assuming these two are right angles. So two triangles at play where these two are two right angles, whereby I'm gonna move this triangle over here, whereby the small side there is r, small side there is r, that's 6. The long side there is 20. And what I have here, from here to here, that's actually the h. Now, with similar triangles, I know that small on large equals to small on large. So right now, I'm missing this side up here where all I need to do is, if the long side is 20, that's h. This side here must be 20 minus h. So pretty straightforward. So off to the side here, using similar triangles. Now, most schools don't need you to, I guess, prove this. In fact, under the new syllabus for advanced, geometry is out. So similar triangles as a proof may not be required, or marks may not be allocated to it. So just use similar triangles by observation, where you basically say small on large, so r on 6 equals to small, which is 20 minus h in this case, on large. So there's a random dot here, so I'm just going to remove that. Cool. What am I trying to do? I need to replace h with r. So I'm going to try to make this h here the subject. So pretty straightforward. Times the 20 up. So 20r on 6 equals to 20 minus h. This simplifies to 10 on 3. And then basically make h a subject. So 20 minus 10r on 3. And that feels like something we can then sub into here. Let's have a glance at what we need. So it looks like what they need, they've common denominated everything, and it looks like they've also factorized the expression. So you know what? As a smart thing to do, before I actually sub it in, I might common denominator everything, and then at the same time factorize the 10 out as well, just to make my expression a bit cleaner. So you can see now it looks very similar. The 10's there, the 6 minus r, and the 3's there. This would be a cleaner expression. Just sub into this value of r here. So I'd say therefore volume equals to pi r squared. Show the substitution. Your teacher loves that. Oops. All on 3, and then you can conclude therefore volume is 10 pi r squared 6 minus r all over 3. Beauty. There you go. 3 marks for that. So good value based on similar triangles. Now, so I'm just going to shift this slightly up. Gives me a bit of space so I can actually work with doing part 2. Now, so what am I doing? Remember the 4 steps in the framework for this second question, where differentiate, solve, test for max min, and then answer the question. In this case, find the values of r and h, right? So pretty straightforward. Now, a lot of the times, whenever they get you to do an expression, it's not the cleanest expression to differentiate just as is. So what I'm going to do to make this guy a bit easier to differentiate, I'm just going to expand it, right? Expand it. So for part 2. So expand this slightly. So basically, it's just using your, I call it rainbows. Some schools call it expansion, foil, or whatever. Expand that. So that's 60. So that's like 20 pi r squared minus that times r. So that's like 10 pi on 3 r cubed. Now I like that because it is just like a polynomial to differentiate, where the 20 pi and the 10 pi and 3 are constant. So step 1 done. Step 1 hasn't been done. So now I've got to do step 1 where I differentiate this expression. So dv dr, bring down the 2. Pretty easy. Bring down the 3, which is nice because then it cancels out. Step 1 done. That's the derivative, right? So I'll put a little box around it because I might want to, considering how easy it is to differentiate, and I might use a second derivative later to test for max min. So step 1 done. Step 2, let it be 0. In which case maybe factorize the 40, the 10, the pi, and the r from both expressions for, so that's gone, minus r equals 0. Is that right? Let's see, 10, 4, perfect. So r equals to either 0 or 4. Obviously, we will not test the 0 because we need the R to be a number. So let's see. So R equals 4 is what I'm going to test for max min. So step 1, differentiate. Step 2, solve. Step 3, test for max min. So very easy to differentiate. Again, so I'm going to actually find the second derivative here. So let's see, d squared v dr squared. That's constant, so it just becomes 40 pi minus, bring down the 2, that's 20 pi r. Right, that's the second derivative. So I'm hoping that when I sub in 4 here, now what do I want? I want a maximum. Maximum implies that the second derivative is negative. Right. So I want this, I can see when I sub 4 into r, that's 40 pi minus 80 pi, definitely a negative. So when r equals to 4, second derivative dr squared is equal to 40 pi. Show your teacher the substitutions and put the 4 in there. So 40 minus 80, that's negative 40 pi. And since pi is a constant, that's positive. This is always negative. Therefore, max volume. Yeah, so step 3 done. Test for max min. Step 4, max volume when r equals to 4. Now, is it 4 meters? Centimeters, with centimeters. So answer units. And also they want h as well. And h equals 2. Now, where do we get h from? This expression up here that we did previously. So just off to the side. So when r equals to 4, what's that? 20 on 3? Yep. So you can say 20 on 3 centimeters. And that's it. That's it. So I'm just going to highlight that expression there. That's my final answer. 6 marks. Not bad, right? So I say it's slightly harder than your usual because it utilizes, well, in this case, similar triangles. When you've seen this question a few times pop up and you sort of understand how they do it, it actually becomes quite easy and quite predictable. So 6 marks there. Let's move on. Now, the next one is a classic difficult question, right? Now, firstly, it's hard because it's got no diagrams. Right, it's got no diagrams, it's got no sort of illustration for you to work with. So you just got to dig through all these English and numbers to draw out and extract out the key information. So it's a classic, I call it the fuel question or the gas, right? Basically, in this case, you got 2 sailors are paid to bring a motorboat back from a harbor, from an island to a harbor. So, I mean, if you had to sort of highlight key facts there. So they need to bring it back, right? So they go to the island and then back. So it's a 2-way trip and the distance, total distance is 1,200. Now, sometimes this can be made harder slightly by saying that instead of giving you total distance, so that total distance there is to and back. So sometimes it can be harder when they sort of give you that the distance between the harbor and the island is 600 and you gotta actually double it. So just to get rid of the ambiguity. So total distance is 1,200. Now, first fact. So they are paid $25 per hour for the time spent at sea. So however long they take in the ocean on to do this job, $25 an hour. And the boat uses fuel at a rate of 20. So this is fuel rate, right? At 20 plus v squared on 10, where v is the speed of the boat. So there's a lot of highlighting here because there's a lot of facts. So, and then diesel fuel costs $1.25 per litre. Now, wow, that's a lot of information, right? So let's see, let's break this down. So you got 2 sailors. They travel to a place and back. They get paid $25 an hour while at sea, but also there's a cost to running the boat because there's a fuel cost, right? They use fuel at this many litres per hour, and fuel costs this much per litre. Okay, now that's important because what you want to do for part 1, let's have a look at what we need to do. Show that the total cost to the owner, right? So the total cost to the owner equals to that. And then part 2, find the speed that minimizes cost, right? And determine the cost. Oh, it's a double question. Be careful about that, right? Speed that minimizes the cost and the cost itself. Okay. So for part 1, we need to find total cost. This is absolutely key, right? So let me just zoom in again. So total cost equals to capital C. Now, can you extract that from the information that there are actually 2 types of costs? There's one, let's call it the labor cost, right? So whatever number of hours they spend at sea, $25 an hour is the cost. So part 1, let's call it labor cost, right? And the labor cost is basically $25 per hour. Now, so it begs the question, how many hours were they actually at sea? Can I, off to the side, or maybe at the top here, write down speed equals the distance over time, right? That is the connection here, yeah? Because time is crucial. Because I've got speed in all of this to be v, right? That's v, yeah? That's this piece of information here. And the distance in all of this is 1,200 kilometers. So how much time, how many hours did they actually spend at sea? So from this illustration here, from this little demonstration of speed relationship, I got time equals the distance over speed, which for our purpose here, the total time at sea would be 1,200 over v. That is crucial, right? That number is crucial because for each hour spent at sea, it's $25 that the owner needs to pay. So the total labor cost equals to 25 multiplied by 1,200 over v. Yeah, which gives us, now I'm hoping if you do that on your calculator, what's 25 times 1,200? 30,000 over v. So that's one part of the total cost. 25,000 times v. Actually, let me see. I got this wrong, right? I read this wrong. So a total distance of 12,000. So if I had the harbour over here and the island over here, I believe that's 1,200 kilometers. So I need to do a return trip, right? So whatever it is, $25 an hour, I need to multiply this by 2. Is that right? Yeah, times it by 2 to get 60,000 on V. Yeah, it's a return trip. Yeah, it's a return trip. So total cost, labor cost is first part, and then plus fuel cost. Now the fuel, the boat uses 20 plus V squared on 10. That's, once again, crucial because I need to multiply that. That's each hour. I need to multiply that by the number of hours, which is 1,200 on V. And then I need to basically multiply it by 1.25. Let's see. So fuel cost, let's say, equals to, let's say fuel equals to, now let me write down the formula and then I'll basically denote what it stands for, right? So 20 plus V squared on 10, that's how much fuel is used per hour. Now, if I multiply that by the number of hours, so the time up here, 1,200 on V, right? That gives us, and maybe I will highlight that. That's the fuel, let's say, used or consumed, yeah? And then I'm going to multiply this by, so that's how many liters of fuel is used, multiply that by 1.25, which is the fuel cost per liter. Does that make sense? So basically, I need to multiply that to get the total fuel cost. Now let's see, 1200. So let me type that in my calculator. 1.25. That's like 1500 over V times 20 plus V squared on 10. Okay, now if I look at that expression and I add that to that, I should get total cost. So maybe just to make my life a bit easier, I might even expand this. Right, so times that by another 20. Let's see, another 30,000. You know what? That's absolutely perfect. So I'm just expanding this expression. It's perfect because I can see 30,000, 60,000 gives me my 90,000 there. And I'm hoping when this guy times this guy, I get the 150 V. Let's see, the V's cancel out, perfect, 10, perfect. 150 V. Yep, so I got two expressions here, which adds up to my total cost, right? Labor cost plus fuel cost equals to total cost. So therefore, I can conclude C equals to 60,000 on V, right, which is a round trip, right, of 1,200 kilometers each way, plus 30,000 on V, 150V, which basically reflects fuel cost, and therefore C equals to 90,000 on V plus 150V. Now, that is basically the hardest part of this question. So a lot of the times, the hardest parts is in the next part where we differentiate, etc. But in this question, absolutely, without a doubt, proving that expression is the hardest part. Because once we get that, we go back into classic mode where we basically do the 4 steps for part 2. We differentiate, solve, test for max min, answer the question. I'm gonna sneak in the working out on this side. Let's see if we can use this space over here. So part 2, differentiate. Now they want to minimize, so I'm expecting the second derivative. If that's the case, should I differentiate again? Yep, easy to differentiate. Second derivative to be positive. So let's have a look. So dc on dv. So it looks like I'm going to find the velocity, which basically minimizes the cost. So dv dc, dc dv, differentiate this now. If you picture this expression here as 90,000 v minus 1, then I can basically say, bring down the negative 1, so negative 90,000 v minus 1 from the power. Yep, and then plus 150 v, which is constant. That is basically my second derivative, right? And I'll put a box around it. Sorry, my first derivative, which I will then find the second derivative on. So first point, done. Second point, solve. So this is on V, so let me just throw this over the fence and maybe simplify it at the same time. On V squared, so switcheroo there, 90,000 on 150. So let me just quickly punch that in, 9,000 divided by 150, 600. So square root that. So you know what? For our purpose here, let's just square root of that, 600. Let's leave it in nice exact form, so 10 root 6. This is meters per second, I believe. No, kilometers per hour. So that number there gives us the maximum or minimum cost. Hopefully it's minimum, because otherwise we'll be doing this wrong. So once we get that, let's test. Test for max min. So this expression looks to be pretty simple to second differentiate. Find the second derivative, so bring down the negative 2. Now what I want a number that's always positive, right? Which looks to be the case, because when I bring down the negative 2, I just double the constant in front. That minus 1 to the power. That guy goes away, and that is my second derivative, right? Which is v cubed with a positive index. And then if I sub in a number for v, it's definitely always positive, right? So you go at v equals to 10 root 6. The second derivative for cost is 180000 over 10 root 6. Now, whatever that number is, it's always going to be greater than 0. So therefore, minimum cost when v equals to 10 root 6. All right, now, did I answer the question? Not yet. Find the speed. I have answered that bit. Determine this cost. So then all I'm left to do is sub v into our cost formula over here in the green. So what I'm going to do, I wonder if I can buy me some space and I'm going to shift this over a bit. Oops. You know what? I'm just going to zoom in and basically just do my answer over here, if that's okay. Minimum cost when v is at, and cost, minimum cost is, so if you sub v into here, let's have a look, 90,000 on 10 root 6 plus 150, 10 root 6, punch that as your minimum cost. So it looks to be approximately, if you did do that on your calculator, $7,348. Highlight that as your final answer. So most definitely, the hardest part about this question is not so much the second part where we differentiate, test and solve. It's more about the derivation of the formula to differentiate itself. So hopefully that was okay. Very classic question. So if your teacher wanted to throw in a hard question, they most likely would stumble across this if they look through past papers enough. It's so common. So let's have a look at one more question I want to do from James Ruse, where another typically hard question is when there's trig involved. When there's trig, speed, distance, and time, it gives you a challenging question. This question was from Ruse back in 2011, but once again, it's not their question. It is a question that is seen quite often in past papers where you have a situation where there's a bus that starts at the depot and it basically travels along a path whereby a boy, is this right in this case? Is a boy or girl? Peter. Peter lives at a farm and he needs to basically miraculously meet the bus that's traveling at 15 meters per second and magically jump on. So Peter lives at the farm and he needs to travel. So he can travel on a straight road or he can travel across the paddock and then meet the bus at the point P and then hop on. So in this case, picture Peter having like some sort of grappling hook, in which case he's just going to swing on and then start riding the bus. So let's actually now go through the question itself. So I haven't really unpicked all the words. So the farmhouse is 240 meters from the straight road. This tick. The bus starts at the depot. Front gate G farmhouse is 3,000 meters away. So from here to the gate, 3,000 meters. School bus leaves at 8 a.m. 8 a.m. Let's write that in. And travels at 15 meters per second. Brilliant. The bus, let's see, Peter lives in the farmhouse and can run across at 4 meters per second. The bus will stop for Peter anywhere. So basically we'll stop for Peter anywhere on the road, but will not wait. Oh, so it does stop. I pictured it, the bus traveling at 15 meters per second and Peter just has to like grappling hook on. Okay, the bus catches the point at Theta. Brilliant. Look at the marks. So even though it looks slightly different to our framework of part 1, part 2, it actually leads you down the path of, so it's basically splitting part 1 into multiple parts, where at the end of the day, this is part 1 in terms of the framework, where the bits leading up to it, parts 1, 2, and 3, just breaks that part down. So Let's have a look. Show that the time taken from D to P for the bus is that. Find an expression for the time that Peter takes from F to P. And then show that if Peter leaves T seconds after 8 a.m. and he arrives at, he and the bus arrives at P, show that T equals that, and then I differentiate. What is the latest time to nearest second that Peter can leave? For us to, oh, okay, let's see this. So part one, show that the bus from D to P is given by it. Now, before we do anything, just like the last question, whenever we talk about time and speed and stuff, I know that speed equals the distance over time, which means if I switch that around, then time equals to distance over speed. And the reason why that's important, everything we're doing here, the variable of choice is time. So we need to make time the subject. I've got distance, I've got speed. So for part one, we're talking about the bus, where the speed is equal to 15, and the distance is equal to dg plus gp. Now, I don't have gp. I know that this guy is 3,000. I don't have gp at the moment, which is this side here, but I can observe a right-angled triangle here and use SOHCAHTOA, in which case it's probably 10, isn't it? So there's a triangle where that's 240, that's theta, and this is at GP, where 10 equals to GP all over 240. So therefore, GP equals to 240 tan theta. Then you basically take that, you sub it into here. Yep, and 3,000 there, therefore. Time equals to distance over speed, so it would be 3,000 meters plus 240 tan theta. So that's total distance there divided by 15 meters per second. And I'm hoping that if you divide that, hopefully that's 200. And if you do this time divided by this, let me just quickly check that. I'm pretty sure that's the case. 240 divided by 16. Beautiful. Surprise, surprise. 15. Right? If it wasn't, I'd be worried. Which is exactly what you want. There. Yep. Part two. So it looks like, I mean, that's the time the bus takes. Now I need the time that Peter takes. And then we will work out, hopefully, a combined time. So part two. Find an expression in terms of theta for the time taken by Peter to run from F to P. Now, once again, looks like it's SOHCAHTOA because I don't have that distance there, but I do have 240 and I do have theta, and that's the hypotenuse that's missing. And also, you can sort of have a glance at the next one. There's sec in there, which is one on cos. So it feels like I'm going to use, to get that distance there, feels like I'm going to use SOHCAHTOA. So for Peter. Now, once again, his speed is 4. His distance is just FP, which is missing. So to find the time, I need to find this distance. So this distance here, once again, it's the same triangle. That's 240 there. The only difference is that I need FP here, right? Where I can see cos theta equals to adjacent on hypotenuse. Make FP the subject. 240 over cos. So let's re-express that because it looks like I need that downstairs anyway. So 240 sec theta. Put a box around that. That's absolutely beautiful. Sub that in. So therefore, time equals to distance, which is 240 sec theta over speed. Therefore, actually, maybe I just go equals to 60 sec theta, which, I mean, looks right. Put a box around this as well. Looks right because if you have a quick glance downstairs here, looks like the 60 sec theta is there as well. So that's part 2. Let's do part 3. Now part 3 is a bit tricky in terms of the language and the context. So let's have a look. If Peter leaves home t seconds after 8 a.m. and he and the bus arrive at P at the same time, right? So he leaves t seconds after, right? So we need to basically set the 2 times of meeting at the same to be the same. So this is what I'm going to do. So I know for the bus to reach this point P, that's what part 1's all about. The time, maybe I'll set, all right, time equals to 200 plus 15 tan theta. I know that. And for Peter, now normally he takes 60 sec theta, but he leaves capital T seconds after this time. So his time is not only the time it takes to cross the paddock, but it's actually T plus 60 sec theta. Hopefully that's okay because he leaves after. And then all I got to do is set these two to be equal. And it looks like if I throw the 60 sec theta on the other side, I got it. So for part 3, it's the concept that is hard. The mathematics is actually really easy. So I'm going to set these two to be equal. I'll set Peter's time on the left, so it makes it easier for me to throw the 60 sec theta on the other side to make t the subject. And then throw this guy over. T equals to 200 plus 15 tan theta minus 60 sec theta. And I have it. So that's step 1 in the framework done, where in this case, step 1 has 3 parts worth 4 marks. Done. And now I'll go to differentiate. So it feels like, when's the latest time? It feels like I need to differentiate, find the value of theta that gives me maximum time, sub theta in to find the actual time, and then add it to 8 a.m. to get the actual time that Peter needs. So I'm going to utilize the next slide, which is a straight copy of the question, just gives me more blank space. So I'm going to differentiate this guy in terms of theta. So part 4. Let's have a look. So the capital T over d theta, 200's gone, constant. Now differentiating tan, we know it's sec squared. Differentiating sec, we know it's sec tan. Yep. So that's a derivative, off the bat. Step 1 done. Step 1 done. Let's have a look. Step 2. So let me make sure I differentiate. Yep. Step 2. Solve. Now, how do you solve that? Maybe factorize. Looks like I can take out a 4, and I'll take out sec. So 4 sec theta becomes 4 sec minus, what's that, 15 tan. Feels like I've got 2 solutions, haven't I? This guy equal to 0, and this guy equal to 0. Now sec theta, this is going to be 0 anyway, so 1 on cos. Yeah, okay, so no solution there. Because it's 1 on cos, and the cos multiplies with the 0, goes away. Yeah. So this guy here, so let's say throw the 15 tan on the other side. Now they're both over cos, aren't they? They're both over cos, so you can actually cancel that out. So it's like 4 on cos equals to 15 sine on cos. So therefore, sine theta equals to 4 on 15. Just keep in mind that everything we're going to do now is going to be in radians, right? Because then that is the inverse sine of 4 on 15. Yep. And if you sort of punch it in radians, it's approximately 0.0 Now, if you did it on the calculator, about 2699. Yeah, because for this one, I mean, it looks like it's very complicated to, not complicated, it's a bit more tricky to differentiate again. So I'm just going to use a table method to test for max min. We've got the value for theta, that gives us either maximum or minimum. Step 2 done. Step 3, test for max min. And we're going to use the table method. So utilizing, so test for max min. So utilizing the table method, so I've got theta over here and d t on d theta over here. So I got in here the exact value of sine inverse of 115, which is approximately that. So maybe add something a bit bigger than this, add something a bit smaller than this. Yeah, so punch both of these in the, obviously that gives you 0. And if you sort of did that correctly, I believe that one there is negative 0.0042, is it? And the other one is, excellent, a positive answer, so 6159, which basically implies that it goes positive gradient, flattens out, positive is maximum, yeah? So the conclusion is therefore max time t when theta equals to the inverse sine of 4 on 15. So step 3, test for max min, done. Step 4, let's answer the question. So once you've done that, you're on easy street, because now you just got to find the time he takes after when the bus leaves at 8 a.m. To leave his house. So we're going to sub this value here into the value of t, right, which is that. So if you did this correctly, you should find, oops. So therefore, I believe if you just subbed it in your calculator, you'd find that t, capital T, is 142.17 to 2 dp, which is 142 seconds, which if you divide that by 60 to find the number of minutes that you add on to 8 a.m., that's basically 2 minutes and, is it 20? So that's 142 seconds. Be 2 minutes and, so 22 seconds. So 2 minutes and 22 seconds. And remember, capital T is the time after 8 a.m. So therefore, time is 8:02 and, well, 22 seconds. Maybe you can write it like 22 a.m. That's the final answer. How's that? So this question was a little bit tricky to sort of derive. It's an 8 marker though for James Ruse, which is quite decent. It's a bit tricky to derive the first part to differentiate, which is step 1, 2, and 3. And then we basically follow the framework to differentiate, solve, max min, answer the question. So hopefully, in terms of maxima minima, across the 3 videos, the framework is readily understood and used, and you can see that it's applied in nearly every question that you see for max min. Once you sort of nail down the framework, apply it to these questions, and you should get it. Some parts, part 1 is quite tricky in that to derive the question, the equation for you to differentiate may require a number of parts. Like the fuel question was quite hard. Some questions require you to use similar triangles. Some questions require you to find a relationship between volume and surface area. In this question, it's to do with time, in which case we need to utilize speed equals the distance over time. And then some questions have part 2 been quite hard, like the last video where we did a James Ruse question where the question required us to subsequently find or prove that it's an equilateral triangle. But hopefully the framework works out, and that maximum minima questions are now relatively straightforward in terms of its approach. So if you like that video, please hit the like button, give me a subscribe, tell your friends. Until then, I'll see you guys at the next video. See you later.